Okay, good evening everybody and welcome to Astronomy Education. My name is Colin Hill and tonight I'll be talking about variable stars. So what are variable stars? What causes them to vary? And we'll also talk about how to observe variable stars. So without further ado, I'll get straight into it. If I can get this thing to work. Here we go. Before I start, I'd just like to acknowledge and pay respects to the Gawler people, the traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationship of the Gawler people to country, and we respect and value their past, present, and ongoing connection to the land and cultural beliefs. Right, so variable stars. So variable stars that vary in brightness over relatively short periods of time. There are two main types. We have intrinsic variable stars, and this animation's not going to work like it's supposed to, but imagine that thing pulsating in and out. So intrinsic stars are stars that vary, the star itself varies in brightness. So we have four subtypes: pulsating, cataclysmic, eruptive, and flare stars. And the other type are extrinsic. So these stars, they vary in brightness due to an external influence. The two main types of those are eclipsing binaries and rotating variables, which we'll go into more later. And that animation seems to work. Yeah. So we'll start off with pulsating variable stars. So these are evolved stars. So these are stars that have moved off the main sequence after having exhausted hydrogen in their cores. And they vary through rhythmic expansion and contraction of their outer layers. As they expand, they cool and dim. Now they do this because there's a lot of hydrogen in their outer layers. And as the star contracts, the hydrogen heats up and ionises and becomes opaque. When it becomes opaque, it traps the heat, so the star heats up and then makes the outer layers expand. As they expand, they cool off, and the helium then deionises and becomes transparent and lets all the heat out, so the star then contracts again. And that's the basic mechanism how these pulsating stars work. And if you have a look at the HR diagram here, so the green line is the main sequence, which most stars they sit on. There's the sun there. So when a star leaves the main sequence and when it runs out of hydrogen, many of these become variable stars. And you can see these are the various groups of pulsating variables and where they live on the HR diagram. And we'll go into these in a little bit more detail momentarily. So the first ones we'll look at are long period variables, also called Mira variables after the prototype star of its class. So these are red giants of class M. So these are giant red stars, quite cool, and they have very long periods of variability. And these periods could be anywhere between 80 and 1,000 days. And the amplitude of variation is about 2.5 to 6 magnitudes. So quite a considerable range of brightness. The star is actually brightest when it's at its smallest size, because that's when it's at its hottest. At its largest size, like there, it's very, very cool, and even though it's very large, it's a lot fainter. So Omicron Ceti is the star Mira, as an example, and it has a period of about 332 days, and its magnitude varies from 3.4, which is a moderately bright star, down to 9.3, which is way below naked eye visibility. So you can see these stars do vary dramatically in brightness. And this is just a light curve plot of Mira over probably several years. So see the cycles are reasonably regular. Then we have the Cepheid variables, which are These are yellow giants. So these are hotter stars than the Miras, class F to K. And they have a much shorter period, more like 1 to 70 days, and a smaller amplitude variation as well, so anywhere between 0.1 to 2 magnitudes. So these are massive stars and have high luminosity, and F class when they're at maximum brightness, and then they drop to a G or K at minimum. So they go from like a white star down to a yellow or orange star at minimum. And they obey a very strict period luminosity relationship. So the longer the period, the more luminous the star. So because they have this strict relationship, they're very useful as standard candles for measuring distance. So by looking at one of these and working out its period, we've got a pretty good idea how luminous it is, and by looking at its magnitude, we can get a rough idea of or a pretty good idea of distance. And because they're such luminous stars, we can actually use them to measure the distances in nearby galaxies as well, because we can actually see these stars in nearby galaxies. A couple of examples here is the star Polaris, which unfortunately we can't see from our position on the planet. That's the pole star in the Northern Hemisphere. And Delta Cepheid is the prototype of this type of star. So you can see there, when it's at its maximum size, it is at minimum luminosity. And then when it's at its smallest size, it's at maximum luminosity. And it's a very regular wave shape. So it's very predictable. There's other pulsating variables. We have the Ra Lyrae stars. So these are very short periods, 0.2 to 1 day, and they vary between 0.3 to 2 magnitudes. So these are short period white giants of spectral class A. So these are older and less massive than the Cepheids. Then we have the RV Tauri stars. So these have a period of 30 to 100 days, and amplitude variations of up to 3 magnitudes. So these are yellow supergiants, and they have an alternating shallow and deep minima, and their spectral classes range from G to K. Then we have T Tauri variables. So these are a totally different class of star. These are pre-main sequence stars. So these are stars like protostars that have only just formed, and they're so young that they actually haven't started nuclear fusion in their cores yet. They haven't contracted enough and built up enough temperature in their cores to start nuclear fusion. So they're only emitting radiation due to gravitational energy contraction. As the star is slowly contracting, the gravitational energy of the contraction is converted into heat, and that's what's powering the stars at this time. Now these have huge star spots on them, and they're very fast rotating. So the energy output, even though it's relatively constant overall, from our point of view, as the sunspots sort of rotate into view, they can drop their luminosity as the sunspots come into view. But they are highly variable and erratic in their energy production as well. And also, a lot of them have these circumstellar disks around them as well, which can obscure some of the energy coming out of them. The next class are cataclysmic variables. So these are stars that have had violent outbursts caused by thermonuclear processes, either in their surface layers or deep within their interiors. So the first class of these is a nova, or a classic nova. So these are close binaries consisting of a giant star, like a red giant, and a white dwarf in a very close orbit. So it's so close that the gravitational field of the white dwarf is pulling gas off the extended envelope of the red giant. This creates an accretion disk around the white dwarf, and it slowly spirals in onto the surface. Now eventually this hydrogen builds up to a critical amount, and the temperature reaches the ignition point of hydrogen for fusion. So we end up with a thermonuclear blast that burns off that hydrogen layer that's built up and increases the brightness by 7 to 16 magnitudes during the eruption. Now, this is non-destructive. The star itself is not destroyed, and the star then slowly fades away back to its original brightness over several years. An example is Eta Carina borealis. You've probably heard a lot about this star in the last couple of years. We've been waiting for it to erupt. It's one of these stars that do it periodically, about every 70 or 80 years or something like that. So it takes that long for the hydrogen to build up. So these are the recurrent nova. And there are quite a few known examples of recurrent nova that every few decades or so they'll build up enough hydrogen to create a nova outburst and then slowly go back to their pre-nova brightness. This is sort of a little animation of it back to normal again. Then we also have what's called a dwarf nova. So these also consist of a giant star in a close orbit with a white dwarf. But in this case, the explosion's caused by instability in the accretion disk. It can actually collapse onto the white dwarf, releasing a large amount of gravitational energy. So these aren't as energetic or as luminous as a classical nova, but still put out quite a lot of energy just the same. Then we have eruptive variables. So these are extremely high massive stars. For example, Eta Carina. So these are stars that have got, say, greater than 80 solar masses. When stars are this big, they're producing so much energy that they're actually blowing off vast quantities of their outer layers just through the sheer radiation that they're producing. And they can brighten by several magnitudes in the process during these eruptions. The star Eta Carina, which is buried in here, had a major eruption in 1843, and it blew off a huge quantity of material in this eruption, and these two lobes here are the results of that eruption. And in the process, it became the second brightest star in the sky for about 10 years. Currently it's about magnitude 6, which means it's just on the verge of naked eye visibility. The star itself really hasn't changed brightness that much, but it's sort of, because it's buried in this gas and dust that it blew off, it's obscuring a lot of the light coming off the star. So these stars are very short-lived, and will end up as a type 2 supernova in the not too distant future, cosmologically speaking. And then we have flare stars. So these are red dwarfs that experience huge solar flares. The result is an increase in brightness of 2 or more magnitudes in just several minutes, followed by a decrease to normal over about 10 to 20 minutes. For example, Proxima Centauri, the closest star to us, is an example of a flare star. And, a lot of red dwarfs appear to be flare stars, and this could be a problem for finding habitable planets around these stars because you wouldn't want your star to suddenly increase in magnitude by 2 or more magnitudes over several minutes. It would be rather unpleasant. Right, so then we move on to extrinsic variables. So eclipsing binaries. So these are two stars in a close orbit that periodically eclipse each other as seen from Earth. An example is Algol, or Beta Persei. Now this is a B-class main sequence star and a K-class giant. So we have the K-class giant here and the B-class star, which is the brighter of the two because it's far hotter. And they pass in front of each other every 2.87 days, and drops the brightness by over a magnitude for several hours as the smaller star passes in front of the larger star. And we actually get two dips of brightness. One when the fainter star, the brighter star is in front, and then one when it's behind. So we get two peaks, or a shallow one and then a deeper one, depending on which star is in front of which. We have B-Lyrae variables. So these are eclipsing binaries where two massive evolved stars are in a close orbit. And they're so close that the stars are actually a bit distorted by the gravitational forces between them. And these have got orbital periods of greater than 12 hours. So these two stars are revolving around each other incredibly fast. Then we have W Ursae variables. So these are also eclipsing binaries, and they consist of contacting low main sequence stars. So these are like two solar mass type stars, but they're in such a close orbit that their outer layers are actually touching. And because they're actually sharing their outer layers, they're always the same stellar class, and they're usually between A and K. And both stars are distorted also by gravitational forces. So you can see there they're sort of egg-shaped. Orbital periods less than 12 hours. Then we have rotating variables. So this is a bit like the Tauri stars, where these have got stars with massive sunspot groupings. And as they rotate into view, the overall light output from the visible surface of the star appears to drop. And then we have ellipsoidal variables. So these are also closed binaries. And the stars are non-spherical, also due to mutual gravitation. And as they rotate, the area of their surface presented towards the observer changes. So you can see this orange star here. And when it's side on, we see a lot more of the star than when it's sort of end on. So it puts out, from our point of view at Earth, we see a change in brightness, as you can see by the plot. Now there's a bit of a complex naming convention with variable stars. We use letters R to Z, followed by the constellation name. Then when we run out of letters there, we then go to RR to ZZ. And when we've run out of letters there, then we go to AA to QZ. The first letter is never later in the alphabet than the second letter. And once those have all run out, then we use V335 onwards, because the first 334 use this system. There's a lot of history goes on here. You know, they probably, if they had known how many variable stars they were, they probably would have just stuck with this system here. So some examples here, V340 Cygni or RR Leonis. Now there are some variable stars that have existing Bayer designations, so they retain that designation. For example, Betelgeuse is Alpha Orionis, and that's a variable star. Now, observing variable stars, so anybody with basic equipment, such as binoculars or a small telescope, can observe variable stars. And you can use these charts, which you can get from the AAVSO, the American Association of Variable Star Observers. You can just download these from their website. And if you're looking at your target star here, T Cepheid, there, so it comes up with these little numbers next to each star. These are the magnitudes of the star, so you can use that to do a comparison. So you can look at how bright your variable, your star is, your target star, and you can compare it with the stars around it to work out its magnitude over several nights or weeks. These numbers, 6, 7, actually means 6.7. So that's magnitude 6.7. They just drop the dot out, so you don't confuse it with a star. So that's their website there. So if you go onto that, you can download these charts. And there's also a lot of useful information on that website about how to observe variable stars as well. You can also observe variable stars with a photometer, or by looking at the actual light using a CCD camera, DSLR, or a dedicated photometer. And if you take measurements over several hours, nights or weeks, you can then plot them on a graph and you can come up with a light curve there. You plot the intensity over time. And ASSA actually has a variable star special interest group. It's headed up by David Ben. That's his email address. It's also listed in the bulletin if you're interested. So there are quite a few members in the society who specialise in looking at variable stars, and you can actually contribute to valuable science. Because a lot of the professional astronomers don't have the time to study these stars, so they rely on amateurs to gather a lot of data, and you can actually submit this data to that organisation and contribute to science. So that's a pretty short talk tonight. Do I have any questions? Covered it pretty well. Yeah, one up the back. Yes. It's an extremely faint star, even though Proxima Centauri is the closest star to us. It's magnitude 13.5, I think. So even with binoculars, you can't see it. So you need a telescope. And during these flares, it can increase by a couple of magnitudes, but that's still only 11.5. Still couldn't see it with binoculars. And you'd have to, because these flares are very unpredictable, they're not a regular thing like a pulsating variable, and they only last for like 20 minutes or so, you'd have to be pretty lucky to catch it as it was doing its flare, I would think. Okay, you've actually seen a flare star? Yeah, wasn't Proxima Centauri though? No. Oh, okay, right. Yeah, fortunately, most of the stars in the sky are red dwarfs. So, and if most red dwarfs are flare stars, you've probably got a lot of stars to choose from, except they're all very, very faint. That's the only trick. Any other questions? Yeah, up the back. It was what? Oh, T Tauri. T Tauri stars. Oh, that's a class of star. T Tauri is like the prototype of the class of star. So all stars go through the T Tauri phase when they're forming. So it's just at one point the Sun was a T Tauri star, like 4.5 billion years ago. Any other questions? Yeah, unfortunately, I haven't done any variable star observing myself. These are the things you probably want to talk to David Ben about. I think if you go onto the website, they've probably got lists of stars that they want data on. So you probably focus on those because, especially in the southern hemisphere, because there are a lot less observers in the southern hemisphere than the northern hemisphere. So there's probably a lot of stars in the southern hemisphere that they probably want some data on. And I haven't been on the site myself, but I'm sure there'd be lists there of stars that they want people to observe. But once again, David would probably be able to help you there. Cataclysmic variables, like nova. Yeah, when a nova goes off, they brighten fairly rapidly, probably hitting their peak within a day or so, but then they can take weeks to fade away back to normal again. So the trick is to try and catch them as they're on the rise, so you can see what the peak is. Because if you miss it, the peak only lasts for like hours. The maximum brightness before it starts to fade away. So the trick is to try and catch them before they hit that peak, so you can actually get the light curve from them. Okay. Well, if there's no more questions, thank you very much.